So in chapter 10, we look at modern atomic theory and see how it's related to the periodic table. So we've already looked at sort of the early atomic theory. This is Dalton's atomic theory. And we've also looked at the periodic table. So the periodic table was developed without any understanding of modern atomic theory and the nature of subatomic particles. However, it's good and it works. So therefore, it should be possible to relate modern atomic theory back to the structure of the periodic table. Now, the development of modern atomic theory began with an understanding of what we call electromagnetic radiation, also known more commonly as light, and how that light interacts with matter. So, energy can move through space as electromagnetic radiation, or what we call light. So unlike something like sound or sound that needs to move through a medium, or you can think of energy moving through an electrical cable, electromagnetic radiation light can move through empty space. Now, the cool thing about electromagnetic radiation is that it interacts with matter. And there are really two big ways that it does this. One is that the matter can absorb the energy that is contained within that electromagnetic radiation. And when that happens, the atoms and molecules that are in your sample of matter gain some energy. And if they gain enough energy, they can actually break the connections between the atoms in that sample of matter. And that's exactly what happens when a skin cancer forms. So when you absorb too much light from the sun, in particular UV light, it damages the DNA in your skin cells, and that can lead to cancer. The other way that electromagnetic radiation and matter are related is when a sample of matter loses energy by emission of light. So if I energize a sample of matter and then I allow it to relax and lose that energy, I'll see emission of light. Now, this is probably most commonly seen in, like in a lamp that has a tube of gas that we energize that gas with electricity, and then as we allow that gas to relax, it emits light. Now, it turns out that the color of light that's emitted depends upon the element that's within our tube, within our lamp, and every element has a characteristic set of colors that comprise its emission. So if you look at the emission of light that's coming off an object, you can tell the elements that it's made up of, which is really cool. That's how we can tell what, objects in the sky that we've never been to are composed of. We use this to identify what stars and galaxies and other planets are made of. The other cool thing about emission is the amount of energy that's being emitted, and the color that's being emitted is dependent upon how much energy your object is losing. And so we use this all the time in things like thermal thermometers. So if you've ever had your temperature taken with a thermal thermometer, we're looking at the light that you are emitting. And in particular, we're looking at the light that is being emitted in a region called the infrared. So infrared light is light that we can't see with our eyes, but we can detect with an instrument like a thermal thermometer. So light can be considered to be a wave, and every wave has three things that define it. They have a wavelength, which is just simply the distance between two peaks. It should also be pointed out that that is exactly the same as the distance between two troughs. For light that we can see, the wavelength corresponds to the color of the light. So chemists will often use color and wavelength interchangeably. The other thing that characterizes a wave is its frequency. And the frequency just indicates the number of waves that pass a fixed point every second. So kind of think of like if you were standing on a pier or a jetty and you were counting water waves that passed you every second, that would be the frequency of the water waves. Now, frequency is often given the Greek letter nu as its symbol, and sometimes people also will just give the English letter F for frequency. So if you start looking at stuff online, you might see both of those things But this little symbol here, it's pronounced nu. It's kind of like a little V that's leaning backwards a bit. Now, light has a characteristic speed that it moves through space at, and this is really quick. It's 2.998 by 10 to the 8 meters per second, and generally the speed of light is indicated with the symbol c. Often to indicate the speed of just a generic wave, whether it be light or some other kind of wave, they might use v, but for speed of light it's always c. So probably most famous equation that uses this is E equals mc squared. So the frequency, wavelength, and speed of light are related by this formula. The speed of light is equal to the product of its wavelength and frequency. So C equals lambda nu. So if you are given two of these parameters, you can always calculate the third. Okay, so how are wavelength, frequency, and energy of light related to one another? Well, the important thing to realize is that the energy of light increases with the frequency, but the wavelength of light increases as the energy and the frequency decrease. So what we say is that energy and frequency are directly related. As one increases, the other increases. But wavelength is inversely related to the frequency and the energy. So as the wavelength increases, the energy and the frequency decreases. So what I have here is an image called the electromagnetic spectrum, and it's divided into the major segments, which are kind of highlighted in along the bottom here. So at very short wavelengths, we have what we call gamma rays, and gamma rays can penetrate even the hard parts of your body like bones and so forth. Gamma rays are often produced during nuclear decay, during processes that generate nuclear radiation, and they can be used to destroy things like tumor cells. They're very, very destructive gamma rays. X-rays have slightly less energy and slightly longer wavelengths, and X-rays can pass through the soft parts of your body but not the hard parts of your body. So X-rays are often used to visualize bones. At slightly longer wavelengths, we get into what we call the ultraviolet. And ultraviolet light has enough energy that it can start breaking chemical bonds. So as I mentioned previously, too much ultraviolet light can lead to skin cancer. Now, it can't really penetrate very deep into your body, which is why it doesn't lead to other cancers, why your skin is particularly susceptible to damage by ultraviolet radiation. Ultraviolet radiation is the kind of light that gives you sunburn. It's often used in what we call dental curing, which is where we have photoactivated plastics that once we expose them to ultraviolet light, we break a few bonds in there, and that causes the material to become reactive and it sets hard. So you might have had this done if you've ever had a photoactivated filling put in at the dentist. They'll activate it with some UV light, and you have to be careful not to expose your eyes to it. At longer wavelengths than the ultraviolet, we get into the visible, and you might remember that the colors in the visible region follow the sequence Roy, G, Biv, the 7 colors of the rainbow. So this is in order of increasing wavelength. So violet light has a shorter wavelength than red light, but it's always in that order: red, orange, yellow, green, blue, indigo, violet, in order of decreasing wavelength. Beyond the ultraviolet, we get into the infrared. And infrared, we experience that as heat. Infrared light is heat. We use it in remote controls because we can't see it. It's not in the visible region. We use it for night vision, and as I mentioned, we also use it in digital thermometers. beyond the infrared, we get into what's called the microwave region, and microwaves are most commonly used in microwave ovens, but they're also used in things like cell phones and for broadcasting wireless data. So these are all applications of microwave radiation. Beyond the microwave region, we get into what we call the radio region. So obviously, this is the stuff you listen to if you ever listen to the radio. And it's also what we use in MRI machines when we're doing imaging. So some of you guys might be interested in careers in medical imaging or perhaps in nuclear medicine. And so it's really important for you guys to know about the electromagnetic spectrum. PET scans, I should point out what that is. That is a positron emission tomography scan. It's really cool because it relies upon antimatter, which is kind of, sounds like it's sci-fi, but it's for real. And so PET scans are kind of cool. Okay. So in Alex, you will be asked questions about the electromagnetic spectrum, and you just want to find, you don't need one as elaborate as what I had on the previous slide, you just want to find a little diagram that clearly has the electromagnetic spectrum indicated on it. So it kind of goes like this. It goes gamma, just in the simplified version, X-ray, UV, visible, infrared, microwave, radio, and that way is increasing wavelength but decreasing energy and frequency. So if you remember that, you're okay. So radio are your long wavelengths, gamma are your short, and that's pretty much it. Okay. So now, on top of that, I guess it's worth keeping in mind your Roy G. Biv, in case you ask questions about the visible region. And again, that's increasing wavelength and decreasing energy and frequency. So in this problem, it says that you are meant to select one in the second column for the type of radiation with the lowest frequency, and then number them up to the next highest frequency and so forth. So 1 is lowest. So lowest frequency means furthest toward the radio end. So ultraviolet, that's really energetic. Blue, that's next to ultraviolet. Then red, still decreasing in energy and frequency. And then microwaves. So the lowest frequency is going to be microwaves, right? There we are, microwaves. That's going to be number 1 in frequency. And then the next lowest frequency, we're going to back it up. We're going to get to the visible, and then within the visible, so it's going to be red. Then we move through the visible, then it's blue. And then we've only got one left, which is ultraviolet, which is the other side of the visible. So that's that. So that's order of increasing frequency. Now, what we should know is that the order of energy is going to follow the same order as the frequency. But order of increasing wavelength is going to go the other way around. So we want the smallest wavelength will be ultraviolet. Yep, there it is, ultraviolet. That's going to be 1 for that. And then the next one is going to be in the violet. It's going to be the blue end. Blue, then we keep going, then it's going to be the red. Yeah, and then finally microwaves is going to be the longest wavelength. So you've got to be aware that the order of the wavelength will be different from the order of the frequency and the order of the energy, and just not get spooked by it. Just take your time. Okay, so that concludes this very short video on electromagnetic radiation. I hope you found it helpful.